what we are going to cover in the assignment, they'll be very much related to what we're doing right now. And some of the problems would be to take you a little bit further than what we cover in the class, and that's kind of the goal of the assignments. Okay, so I'm going to proceed today into getting into some of the more nitty-gritties or the details of the heterostructure design, and just to as far as how I'm planning to cover this topic of compound semiconductors. So we're going. The material science of it obviously has aspects of, for example, if I mix compound semiconductors of various kinds, gallium arsenide or indium arsenide or gallium nitride and indium nitride, there are many aspects of material science which one needs to kind of understand to be able to kind of mix them in the first place. Meaning, when you form an alloy of indium gallium arsenide or you form an alloy of indium gallium nitride, if you don't do it right, it won't let you do it. Basically, they won't mix. So there's this aspect of stability of an alloy, which is a mixed system of two crystals. That part of the material science we're going to cover a little bit later. Okay. Right now, what we are doing is saying that, look, I have this amazing large range of band gaps, large range of lattice constants, and somehow I've managed to mix them. What are the properties? That's what we're looking at right now. And once we, the reason for that is kind of motivates what you can do with it, and then we figure out how we're going to do it. So that's really the way I'm covering this class. There are other ways to do the course, meaning one can start with here's how we actually make it first, and then what can we do with it. So we're taking the other way approach in this course. So today what we're going to do is look into some of the more details of if I'm able to create, for example, a heterostructure, compound semiconductor heterostructure, which has, for example, let's say I choose a wide bandgap aluminum gallium arsenide or something like that here, let's say, and I know its bandgap, and going back to the bandgap versus lattice constant sort of picture that we had developed. So I can kind of, let's, for simplicity, assume that we have an heterostructure between aluminum arsenide, which is here, and gallium arsenide, which is here. So what's shown here is the band edges. This is the conduction band edge, and you have all your spaghetti EK diagram above it, right? Here's the valence band edge, and you have all your valence bands under it, and all that. So this is the gap, right? And I put aluminum arsenide and gallium arsenide, and there is a band offset between the conduction band, and there's a band offset between the valence band. And band offsets look like this, and I think you realize this is the energy band diagram. This is not the band structure, meaning this is the energies as a function of distance, right? That's what that is. So let's say I put together two materials which have, I'm going to just sketch the band diagram now, and it looks something like this, right? And it could be aluminum arsenide, aluminum antimonide, or something like that. Something like that has a larger band gap, a smaller band gap, and a larger band gap again, and it's a layer, meaning in a three-dimensional geometry, the way it would look is, you have grown the crystal, let's say, along this way, and this layer was gallium arsenide, and then you have this layer was aluminum arsenide. And you have inserted a very thin layer of gallium arsenide, and you come back to aluminum arsenide. This is a very simplistic picture, but it's actually correct. And this is what we're going to call as the thickness of this well, LW. So we're going to look at that. And today's class, we're going to kind of look into some of the details as what happens to the energy states allowed inside the well and all that. And it's kind of a particle-in-a-box problem. But we're going to look into some detail. Especially, we want to develop some intuitive feel for what are the orders of magnitude of things typically when you're designing these things, obviously you can run some code and figure out what are the energy levels. If I do a photoluminescence, what wavelength will I get and all that. But what I want to do by the end of the class today is you should not need anything like that. You can just do it in your head. Well, if I have this much thickness, this is exactly what energy I should get. So that's the feel you should get. And we can do that, with a relatively simple model. We can go and design that aspect. And when you're actually designing devices like this, materials, the material design, the thicknesses and all that, it's very helpful to have a feel for things like that. So, okay, so let's look at what, first of all, the energies are looking like this in terms of an energy band diagram. But what is actually going on in reality, because you realize that inside this material, I will first kind of zoom out a little bit and look at that material and say what is going on in detail, right? Obviously, everything is composed of atoms, right? And so if I look at this crystal now, I can ask the question that if I have an electron that were, that is either inside. What are the allowed energies of the electron if it is inside the crystal? Can it be here? Can it be there? Can it escape the crystal? All that stuff. So let's just zoom out and look at the big picture, and then we kind of zone in and look at the details. So, okay, let's sketch it here, right next to it. So here's my x-axis kind of being sketched along this direction. Right? So what I'm going to kind of sketch is not just the stuff that's going on inside the crystal or the material, but also outside, just to give you again look at the orders of magnitude of all the energies. Okay. So inside this material, I think we realize that there are aluminum atoms and arsenic atoms. So they are periodic. This is obviously in a very not at all to scale. Let's say this is a micron, then you'll have many atoms, and that is constant. So about 10,000s or so on. And inside this region, you have gallium atoms and arsenic atoms. So they are whatever this way, and then you go back to aluminum and arsenics. Does it make sense? The atomic structure. And outside, there's nothing, right? That's vacuum. This is vacuum. Now, you realize now that if I have aluminum atoms here, then it has, every atom, if I take any single atom, it has a potential that looks something like this, right? Right, for the electrons, right? And if I put another one, so the potentials add, and you start, in a crystal, it looks something like that, right? And we have seen before, then you have the core levels and all that, and finally you have all the bands we're looking at are kind of out here. Right? That's what we're really looking at. So similarly here, let me just sketch this part. What we'll have is outside in vacuum, electrons have a certain energy, right? In vacuum. Right? And then here also they have some energy. And now looking at the atomic scale of the problem, the moment you come here, it kind of has a very deep sort of well, right? And you start doing this sort of a business here. Actually, let me do it properly, okay? You kind of, let me do it roughly to scale, but clearly the x-axis is not to scale, so the y-axis is going to be difficult to be scaled. So let's say we have something like this. It gets a little messy now, okay? Something like that. It's just that, right? So it repeats. Similarly here, it repeats. And then when you come to this layer, gallium arsenide, which has a smaller band gap, there's a smaller band gap, actually this goes even lower. Kind of like, let's say this is our quantum well. Does that make sense what I'm saying here? The height to which this potential heights kind of go is smaller for the smaller band gap material. As a result of all this stuff, and then you have the bands here, right? So because of the overlap of the bands, so you have valence bands and conduction bands. So let's say, here's a band, allowed band. Here, I think it'll be a little trickier now because, so let's just look at this band, and then let's look at just this band. Okay, there's a band here. So that's kind of the energy scale of things here. For example, this is the conduction band edge of aluminum arsenide. That makes sense? Compared to vacuum, right? So, and it has its own electron affinity. So aluminum arsenide, so that's aluminum antimonide, sorry, aluminum arsenide. So here's the band edge, and that's vacuum. So that's the electron affinity, meaning from here to here would be electron affinity. Gallium arsenide, electron affinity is a little larger, right? So that's right. And that's conduction band edge of gallium arsenide, conduction band edge of aluminum arsenide. Does that make sense? I mean, this is all the stuff. So you have kind of multiple levels here. What we are looking at is just the one inside here, and we're not really looking at what happens out there. Right? Meaning the crystal already is a big potential well. The moment I put an electron in any matter, already it's a potential well, right? But it's a large one if its thickness is very large. That's the meaning I'm trying to kind of get to. Right? Okay. Okay, good. So then we go and any questions here?
What do you fill in next to the gallium arsenide?
Oh, yeah. No, it continues. Yeah, no, it does continue. Yeah. I just didn't want to. Yeah. So these are the atomic potentials, and so what we are doing is, as you can see, it's what one might call as a mean field sort of approximation. In reality, there's all this potential variation going on at atomic scale. If you look at the real potential here, that is changing very large values. So you also have the slope of a potential is the electric field. So you have electric fields going from zero, very high to very low, and all that. So all this stuff going on. But the thing is, once you form these bands, the electron kind of is not able to see the variations, because its energy is really high compared to all the core levels. Core levels see everything, but they're stuck. They cannot get out, right? But the band electrons are not kind of able to. The potential variations they are seeing is relatively smaller, And I will kind of this idea. So this is in a way the idea I'm trying to get through is this picture that electrons can be in vacuum, then get captured in the crystal, then captured in a quantum well. This kind of permeates, so it kind of scales to, and then we will do design of this problem instead of in this picture. We're going to do mostly in terms of the materials now, right? So already air with a semiconductor is a quantum well, if you might want to think of it that way. That's really what I'm trying to say. So for example, if this layer is extremely thin, molysulfide or graphene, then you have a single, it's a quantum well, two-dimensional layer, it's a quantum well. So, yeah. Okay, so let's move to the next step, and this is something since quantum mechanics is not a prereq in this course, I'm going to just do this in a little detail, because sometimes you probably might have seen it multiple times if you have done quantum course, but there are some small details which are extremely important for compound semiconductor material design and quantum well design, quantum dot design, which don't get emphasized in a typical quantum mechanics course. So we'll just so here's the question. So instead of gallium nitride, let's say we have gallium arsenide, we have gallium nitride, indium gallium nitride, and gallium nitride. Let's say any quantum well or like that. Yeah? And the question now is, what are the energies allowed for the electrons in the quantum well, right? Or in the whole structure, not just in the well, but what are the new energies that are allowed? So what we are going to start with is let's look at just the conduction band edge initially, and ask the question that what are the energies allowed here? And you can see it looks like a potential well. Let's say the barrier height here is U naught, in electron volts. And we'll, typically in semiconductors, and then this is also a rule that I will kind of discuss a little bit later when we look at the material science. But as a rule of thumb, the band, if the band gap of aluminum nitride is, say, E gap of layer A and E gap of layer B, and B is the smaller band gap semiconductor, then obviously we have a, this is the difference in the band gaps, whatever is the difference. And this is a rule of thumb that you can see that the difference has to be split between the conduction band and the valence band, right? I mean, they have to align in a certain way. if the alignment is like this, meaning the conduction band edge, the band gap of the narrow gap material lies entirely within the band gap of the wider gap material. That's one sort of alignment. There are three possibilities mathematically. You can see there's type 2, where it's kind of staggered, and type 3, where it's broken. This is called a broken gap alignment. We are going to discuss the details of this in more later. Okay? But if it's type 1, here's a rule of thumb that the amount, as you can see, it has to be distributed in a certain way between the conduction band offset and the valence band offset. Right? Could be 50-50. Could be, one could be much larger than the other, right? And you can see here, these are special cases where, one has gone negative or something like that, right? Delta EC is negative, but delta EV is still positive, for example.
So what has to be spread out?
The difference in the two band gaps, right? So here's the band gap of A, and here's the band gap of B. And now they have to align, right? So the top line here is the conduction band edge of material A, and here, and then the material B. So they have to kind of align in a certain way, right? The band edges. And because there's a difference in band gap, if it's aligned in this way, called the straddling or the type 1 band offset, then delta EC, which is the conduction band edge difference, let me label those in. Okay, so this is delta EC, it's the conduction band offset. This is the delta EV, or the valence band offset, okay, because that's the valence band and that's the conduction band. Clearly this is what I'm trying to say is clearly this is equal to delta EC plus delta EV, right? And I'm saying there's some ratio of the two, and the rule of thumb is the conduction band offset is roughly, this is a very crude rule of thumb, but it works most of the time, is about 70%. 70% of the band discontinuity goes into the, or band gap discontinuity goes into the conduction band, and 30% into the valence band if it is of this kind. So, a decent rule of thumb, and it works for most simple cases, but this has been tabulated, and the band offsets have been measured relatively accurately, and we'll discuss the reason why about this a little bit later in the course. Okay, so now what we are finding, we're trying to find is what is this barrier height for electrons in this sort of a quantum well, and the answer for that for the conduction band is the barrier height is just this. Give me the band gaps of the two materials, I'll take difference, take 70%, that's my barrier height. Does it make sense? Yeah.
What's the red lines in between?
Yeah. So you mean that dashed line? So this is a very interesting observation made by Chris van der Waal in 2003 and his collaborators, that there are many theories, microscopic theories, that explain what is the origin of the band offset, meaning why do we have this, why do some materials have broken gap and all that. But what they were doing is they were doing computational studies of what energy, if I introduce a hydrogen atom into the crystal, hydrogen atom, what would be the energy of the electron of the hydrogen atom if it's sitting inside the crystal? Right? And they find that for gallium phosphide, for example, it's here compared to the band edges, somewhere middle of there. For indium nitride, it is very deep in the conduction. So they find different energies for different semiconductors, and when they align them all, say let's assume for arguments for whatever reason that the hydrogen level is the same for all, and then obviously it aligns your band offsets in a certain way, and then they find that the band offsets are actually pretty close to what we experimentally measure. So even today, people are not completely clear what is the origin of the band offset exactly. And this was one of the theories they put forward, that it's determined by hydrogen. But we'll discuss this later in detail. So the material science of that in quite some detail later. Okay, so this is a rough order of magnitude, and you can now see that if I take as an example, let's take aluminum arsenide, which is about 2.3 EV, gallium arsenide, which is about 1.4 EV. So let's put that in 2.3 EV minus 1.4 EV, right? So that's about 0.9 times 0.7. That would be, roughly 0.6 EV or something like that. If you choose aluminum arsenide and gallium arsenide. Right? If, on the other hand, and you can see 0.6 EV is actually much larger than room temperature KT, which is 26 millielectron volt at 300 Kelvin, right? So if an electron gets into that well, it cannot be thermally, it cannot escape because of room temperature energy. Because what we're saying is this thing is 600 millielectron volts, right? And this is 26 millielectron volt. And so I think you know that according to the Fermi-Dirac or the Maxwell-Boltzmann approximation, if you give an electron an energy kT, then if you have two energy levels allowed, then the ratio of electron occupation of here and here is given by that. Right? So e to the power 600 by 26 is pretty much infinity. I mean, it's a very large number, right? So there's very little escape. It's going to get stuck there. Right? I mean, that is one of the meanings of quantum confinement as well. So the barrier height is too large for the electron to get away with thermal kicks, with thermal energy. That's the meaning of it. Okay, okay, so now, and you can see now you have a complete freedom in design that instead of choosing aluminum arsenide, you can actually choose, let's say, here, which is maybe 1.7 EV. Typically, this is what's chosen. Typically, what one would use is like 30% aluminum gallium arsenide. So it would be, this 100% aluminum. You kind of come here. You kind of reduce the barrier height for various reasons, and those reasons we can discuss later. But let's say we, instead of, let's say, because you're designing, let's say you want 0.3 electron volt, 300 MeV barrier height for whatever reason. Then you can obviously back out what should this be, right? And then from here, you can choose what composition aluminum should you use, and you go and actually grow that structure chemically. Right? So that's the design back and forth one goes through here. Okay, let's say we have done that. We have grown a quantum well, and now we are asking this question of what are the energies for the electron. Okay. So what we'll start with is a very simple problem, one of the most basic problems, the first problems you do in your quantum courses, which is the particle in a box problem. Say that instead of 300 millielectron volts, instead of 600 millielectron volt potential well, this is a finite potential well. I'm going to assume first that the barrier height is infinite. I'm going to just assume it's infinite first. Okay? Then what are the energies allowed for the electron in that one? And then I'm going to come back and make it finite and see that what we'll see is that obviously the answers will change, but not much. And that's kind of nice, because right away, for the infinite well, your answers are very simple, and that's something you can remember. It gives you a very strong intuitive feel. And then you make it finite, and you say that, well, I know that because it's finite, the energies will be a little different, and then that's what we want to kind of look at now. So the infinite well problem is again, because we do not have the prereq, I'm going to just go through it once, and as we go through it, I'll point out the little details that are actually very important for the semiconductor design, and typically may not be emphasized in a quantum course, but in semiconductor device design, for example, when you're growing structures like this, it assumes special importance. Okay? So, what are the energies allowed? What we're going to do is, you realize in this picture that the electrons are, so if the electrons are moving in this direction, only then they see this well. Right? It's a very important point. Only when they're moving in this direction, that's when they see the well. If the electron was somehow in aluminum arsenide and it was moving this way or that way, there is no well there. So this is a 3D crystal. And the heterostructure is along one direction right now. That's what we are looking at. So meaning the quantum well is actually along one direction only. If we had a situation where so instead of doing this, let's say what I chose to do was, instead of a very large area in the cross section here, I chose a very narrow region, and that would be, for example, a nanowire. You can actually make this crystal. Instead of being like that, you can make it, a very narrow diameter, and so let me just sketch it. And then you put in a very narrow disk or something like that of gallium arsenide, and then you have aluminum arsenide and aluminum arsenide. Right. So we are kind of so we made this very, very small, maybe about few nanometers in that direction in diameter. So that's a quantum wire or a nanowire. And inside it, you now insert that disk and the electron moving this way. So now that's more of a one-dimensional problem. And this dimensionality aspect is rather important. In this situation, the electron is free to move in these two directions, but in this direction, it has a quantum well. In this situation, it is only free to move in one direction, and in that direction, there's a quantum well. Does this make sense? I mean, so it cannot escape the well here. Right? Right. So this is a 1D problem, and the different dimensionalities of this, we'll discuss that part later. But let's look at this problem, which is a 1D problem, and there's no complication of lateral motion at this point. So what we're looking at, therefore, this is an example, but I don't need to erase it. It says it's a one-dimensional quantum well. Okay. So this is, a higher dimensional quantum well. What we'll find is the answers we learn here will obviously apply to the 3D, but then there'll be free motion in the other two directions. So that's a small detail here. Okay. So what are the energies allowed? I think we kind of know that if you want to find the energies of anything, what you do is of an electron, for example, what you do is basically you add the kinetic energy plus potential energy is equal to the total energy. I mean, that's something we know, right? I mean, kinetic and potential energy. You add them up, you get the total energy. And in classical mechanics, the kinetic energy is p squared by 2m, plus potential energy is whatever, if a ball is rolling down a hill, it's the hill's potential, or whatever that is, and that's the total energy, right? That's classical mechanics. But I think we know by now, after 100 years of development and understanding, roughly 100 years of development and understanding, that electrons, not just electrons, everything behaves, has a wave-particle duality, and that's the heart of quantum mechanics. It says that your everything, including electrons, is not just a matter, but it also has a wave-like nature. And because of that, these relations get slightly modified. And let me just write that down. You have Planck's constant appear, which is the essentially anything quantum will always show that. And instead of writing plain energies, what you have to first find are the wave functions for the electrons, and you have to solve this equation. You can't just add two numbers now. Because of the wave-particle duality, the momentum, which we had written as p, and the x, they do not commute anymore. I mean, there are some details of that, and we're not getting into the details at this point. Here's the equation one needs to solve, and that's what we will solve. So what are the parameters here? Very importantly, if the electron was completely free, there's a mass of the electron here. If you're solving for the electron motion, for example, inside a SEM system, or electrons going through vacuum when you're doing STM measurements, then this is the free electron mass, because the electron is truly free. If it was out here, then the mass would be free electron mass. If your electron is in aluminum arsenide, this is the effective mass of aluminum arsenide, effective mass now, because the atoms and all that, all they do is they create the EK diagram, right? And then here in vacuum, it has a certain mass. Inside the semiconductor, it gets renormalized. It gets a slightly different mass. That's the meaning of effective mass. So the mass that goes here inside a crystal is effective mass, not the free mass of the electron. So it's called the effective mass theorem and all that. But very importantly, you have to be sure what you're solving for. If you are looking for electron energies in the conduction band, you use the effective mass of the conduction band. If you are looking for electron energies in the valence band, you must use the effective mass of the valence band. Right? And similarly, you must use the valence band offset, not the conduction band offset, and all that details. Just be clear about which band are we looking at. Okay, and the potential is it is the potential that electron sees. And right now, what we're looking at is a 1D infinite quantum well. What does that mean? Here's the problem. Again, please read this up in Rocket's book. So what we're looking at is here's x, here's plus L and minus L, and on the left side and on the right side, the potential barrier height is infinite on both sides, and then potential is 0 between minus L and L. Makes sense? I mean, that's really the problem. And remember, if there was if there were no potential barriers, what would be the energies allowed? Then your V of x would be 0, right? If there was no potential barrier, and from that solution, then you can write down right away. You have a so the solution is you need to find the wave function that represents the electron. It's exactly the same as Maxwell's equation. If you want to find the energy of in an electromagnetic mode, you have to solve an equation, and what you solve for is the electric field or a magnetic field, right? I mean, you have the wave equation here. You solve for electric field or magnetic field. Why? Because the field has both amplitude and phase, and any wave you will have to solve a wave equation, and this is the wave equation of matter. I mean, that's quantum mechanics, right? So that's the heart of the problem. So you're solving for the wave function that represents the electron that has both an amplitude and a phase. Okay, so now the potential is if there were no such potential, this is infinite. Basically there's no infinite potential, it's free electron. Then you can right away show from V of x is equal to 0 situation that a wave function would be something like e to the power ikx, and energy would be hk square by 2 times the free electron mass, right? And that's it. I mean, you've completely solved the problem, and all energies are allowed. H bar k would be the momentum of the electron, where k is 2 pi by the wavelength of the electron. And 2 pi h bar is Planck's constant, h over lambda is momentum. That's de Broglie relation. I mean, that's the heart of quantum mechanics, wave-particle duality. So that's the equation of a free electron. That's the solution of quantum mechanics for a free electron. It can have any wavelength, it can have any energy, it can have any momentum from these relations, right? It can have any wavelength. But why? Because you don't have to fit into any box. There's no potential barrier anywhere. It can stretch out or do anything like that, right? Obviously, once you put it in a box like that now, you can see right away that an electron, which is a wave, just like if you put 2 mirrors and you have light going back and forth, they get localized, right? I mean, the light bounces back and forth. Exactly in the same way, the electron states that can exist in this well will be states that go to the right and go to the left, and then they interfere one way or the other. So these are basically electrons rattling back and forth and interfering. And the ones that fit exactly right inside this, satisfy all boundary conditions and everything, are the ones that will be allowed here. That is really the solution that will tell you what are the energies allowed, what are the functions allowed, and all that. Does that make sense? I mean, at least qualitatively, that's clear. And now V, which is the potential, you can see now for the infinite well, the potential is 0 here. V of x is equal to 0. And outside here, V of x is equal to infinite, right? V of x is infinite. So it's 0 for between inside the well and infinite outside the well. Right now, right away, you can see that if you have 0, your solution must be very similar to the free electron solution, right? Because here this is V is equal to 0. But now you realize that you cannot have just one k, meaning this is actually a wave going to the right. You must have a combination. So let's label these regions. This is 1, this is 2 inside the well, and this is 3 on the right side. The three regions of the well, right? So in region 1, Actually, I just talked about region 2. So in region 2, V of x is 0, right? No potential. And what I'm saying now is we can kind of look at this solution and say, well, I know this is a solution. Because if you substitute e to the power ikx in psi, and you take a double derivative with x, you will see that you will get the same function times a constant outside. You'll get it, right? Does that make sense? If you take e to the power ikx, and you plop it in here, this is 0. Take double derivative, it will pull out 2 ik's to the front, but it will leave e to the power ikx as e to the power ikx. No matter how many times you differentiate, it's going to leave it like that. And that means that whatever function you started with, you pulled out some constants in the front, you get the same function again, and that's with some constants in the front. And what's that constant is just that energy, right? That's the eigenvalue, or those are the allowed energies. Now, what I'm saying is the same deal, except now, because it's inside a well, and we physically reason that it must have right-going and left-going waves, one must choose, instead of just e to the power ikx, which is a right-going wave, you must choose a left-going wave too, and leave that possibility also. So you must choose both left and right-going waves. Okay. And then you take that, you plop that in again, and you will see that this will still satisfy. Any linear combination of ikx's will always satisfy that equation, right? It will always give you a square k square by 2m as the answer. Right? Always, right? So, okay, so but then the most interesting part of this problem is because v of x is going to infinity in region 1, and v of x is going to infinity in region 2, in region 3, what happens there? What happens there, right? So now you see that on the left hand side, you have, this term is blowing up, it's going to infinity, right, for those regions, right? The potential term is blowing up. And I think you can reason this out. There's only one way that this equation can still be satisfied, with a finite energy on the right side. Okay? Finite term on the right side, and that is if psi is 0. Psi is 0, meaning the wave function cannot exist outside. And that's the only solution for this problem. And from this argument, you say that psi of x is equal to 0 here, and psi of x is equal to 0. And if it seems a little not that clear, what you can also realize is what quantum mechanics tells you, just like electric fields in Maxwell equation, square of the electric field is the energy in Maxwell equation, square of the wave function in quantum mechanics is kind of the probability density of finding the particle, mod psi squared. Right? Mod psi squared must be 0 in a region where the potential is infinite, because there's no chance electron is making it there, right? And if mod psi squared is 0, psi must be 0 too. Right? So that's clear, right? So yeah. Anyway, so that basically already determines what you need to do to solve this problem now. That's basically a boundary condition. This is a boundary condition that psi of the wave function must go to 0 at the two edges, here and here. And it must oscillate like that. It must be an oscillation in between the two. And by matching the two, basically at the two edges, at plus L and minus L, you can now recover all the energies allowed. That's the eigenvalue problem. That's not. Okay. Hopefully you've seen this, but any questions here? So let me just do that once, and then we'll look at the finite well problem, which is obviously the more pertinent one here. But I think the infinite well problem is interesting itself. So you can see now that the wave function here at minus L and plus L, right? So it has the wave function. I'm just plotting the psi, for example, has to go to 0 and 0, it's like, right? And inside it can wiggle, right? It can be like that, it can be like that, right? And we write, so inside that we already have this solution here. We can write that at psi at plus L, right, will be a e to the power I k plus L plus b e to the power minus I k plus L. It must be equal to 0, right? And psi at minus L minus I k L b e to the power plus I k L is equal to 0, right? That makes sense. Just saying that at the edges it's 0. That's it. Whenever you have an infinite well, there sometimes you see that in you also match. Sometimes you match the what do you call the derivatives, but in an infinite well case you don't match it. I mean, it's really discontinuous because the slope suddenly kind of goes like that. It's not continuous. You don't match it. So okay, yeah. So this is it, and from here, what you basically recover right away is. So you see, kind of these are two equations, right? And A's and B's are unknowns, okay? And K is kind of unknown too. But what you realize is for these two equations to be self-consistent, the determinant should be 0, right? I mean, the A's and for A and B to have non-trivial solutions, you can see right away A and B being both. If both are 0, this is obviously all true. But then we have nothing. I mean, basically that's what's called a trivial solution where there's no physics there, because if A and B are 0, there's no particle. I mean, the wave function is 0 everywhere. There's no particle. So that's not what we're interested in. We are interested in situations where A and B are not 0. And therefore what you do is these are the coefficients, okay, and you basically take e to the power ikl, e to the power minus ikl, basically just write them as a determinant, right, and that should be equal to 0. This is the condition required for A and B to have non-trivial values, meaning finite solutions, right? Is that clear? I mean, this is one way to look at it. You can actually just run through the math and all that. But essentially, if you do that, you multiply this minus multiply that, you get 2ikl minus e to the power minus I 2ikl is equal to 0. End result of all that business is e to the power 4 ikl is equal to 1. That's your solution, right? So that's basically telling you what k's are allowed, what k's will be allowed for this problem. And from here, I think from complex analysis that basically from e to the power I theta, this is your phase. This must be equal to some integer times 2 pi. Right? Must be equal to some integer times 2 pi, and therefore you realize that k will be some integer times 2 pi over 4 times L, and I am going to label as kn. What it's saying is not all k's are allowed now. So only certain k's are allowed. What does that mean? Only certain wavelengths are allowed. Not all wavelengths are allowed. These are the wavelengths. These are the wave vectors that are allowed. You can turn it upside down and write it as 2 pi over the wavelength of the nth mode. It's just that. Right? I think it's better to maybe write it in a slightly different way. 4L, the width of the well is 2 times L, because we have chosen minus L to plus L. So we can write it as 2 times the length of the well, and then the 2 and the 2 go away. This is a very nice thing to remember. If your well width is LW, it's whatever nanometers, 2 nanometers, then the k's that are allowed are pi over that length times an integer. That is it. I mean, that's the solution. And what we'll show now that the solutions that are allowed here are all n's except n is equal to 0. So n is an integer except the integer is 0. So plus 1, plus minus 2, all those are allowed. 0 is not allowed. Why? And you can go back a little bit and see that, because when you put n is equal to 0, again you will get psi is equal to 0. And then that's a trivial solution that doesn't give you any physics. Okay. In pictures, what has happened here is you will realize that if that is so, you take n is equal to 1. Then at n is equal to 1 plus 1, let's say, k is n, it's basically pi over L. Right? So as a result, 2 pi over, I'm looking at lambda 1 now, okay? This k1 is pi over length of the well. Forget about k, I want to find out what's the wavelength. Okay? So that gives you right away that the wavelength of the first state, this is the ground state of the system, is basically, so pi's go away, you get 2L width, twice the width of the well. That's the ground state wavelength. Now you can see wavelength is a weirdly defined concept. What it's saying is the wavelength, if the electron were actually free, it would be kind of twice the width of the well. This is the width of the well, this would be the full wavelength, but this is the wave kind of starts out, but it kind of never makes it to a full oscillation because it's bound. So it's, right? That's the ground state. Go n is equal to 2. It will have a node now. It will actually go through a full wavelength. It's a node at the center. Okay. So n is equal to 2 will have, as you can see, there will be 2 here, and therefore this 2 goes away, and lambda 2 will be basically just the quantum well width, and so this is a full wavelength. And so, is that here? I mean, this is a simple thing, but yeah. Kind of important, and you can see now the matter is really we went through all this math to get this, but you could have written it down just from this intuitive picture that the particle must wave function must die, so for the only k's that are allowed are the ones that will fit. It's the wave fitting that can immediately give you the answer. What I'm saying is for the infinite box you can skip all this and just say that if I give you the well width LW, then 2 pi over, or basically n times lambda over 2, lambda is the wavelength of the nth, is equal to the width of the well. That will give you all the answers right away. Wave fitting procedure, basically. Okay, so now obviously what we're interested in very much are the energies, right? Energies of the electron. Two things, energies, wave functions are very important, but even more important is what is the symmetry of the wave function. It's very important for compound semiconductors. And let's just write that down, okay? So now the nice thing about the particle in a box problem in this nature, especially in the 0 region, when the potential is 0, is the energy is h squared by 2 effective mass times d2 by dx squared times the wave function, and this is true everywhere at all x. It's true everywhere. And now you'd take advantage of the fact, basically this plus v of x, right, times psi of x. This is true at all points of x. This is your Schrodinger equation, really. But you take advantage of the fact that inside the well, my v is 0. Right? So you put v is equal to 0. And inside the well, you know your psi now, because you've written down it's a to the power ikx plus b to the minus ik. So you know that too. Plop them all in. What the answer you get is h squared kn squared by 2 times the mass of the electron, effective mass of the electron. This is the nth energy level that is allowed. This is quantized energy levels now. N is that integer, and it's the quantum number that represents that number. So, okay. And from here you can now obviously substitute kn. We just found it's n times pi over the length of the well, right, whole squared. So En becomes h squared, pi squared over 2 effective mass L width squared times n squared. Now this is probably kind of the, as I was saying earlier, you need to develop some intuition. This is one of the things that you really need to know the intuition for. I mean, I'm going to look at numbers now for this. Okay? So what it's saying is the ground state is put n is equal to 1. You get ground state energy there, right? And that, let's call that E1. First excited state is E2, and so on, E3, and there are infinite number of states. All the states are below the potential barrier height because the potential barrier height is infinite itself. So that's the meaning of this problem. Okay, Now, let's put in some numbers. So the way we typically write it is nth eigenvalue, nth energy allowed is n squared times the ground state. You can see that. I mean, this is the E1, right? It's n squared. So it's increasing as n squared. And because it's an infinite well, typically this is labeled as E1 infinite. Infinite potential barrier height. This quantity here is labeled as E1 infinite. Okay. Now, if you go back and just look at all the n values, and what you see is you get clearly you get this is an even function around x is equal to 0. This is the odd function, and you get right away that if you substitute the values of kn's, what you get is these the even ones go as cosine, obviously, because at 0 it's max. Cosine, sine, oscillating faster. As n increases, your period decreases. The period changes. Okay. So basically you alternate between even and odd, and so on. Symmetry is important. So this is what will happen in the conduction band, and you'll get the same business in valence band too. The first state will be even, the second state will be odd, second state will be odd, and so on. Okay, so numbers. Okay, E1 infinity. I'm going to substitute here. You can put in values of Planck's constant, pi, and all that. Effective mass. Okay, let's write effective mass as, for argument's sake, is just 1 for now. Okay, and quantum well width. Let's assume I have a 10 nanometer width. Okay? Let's assume 10 nanometer width. And if you plug in all the values, what you will get then is E1 infinite. Here's the expression. I think I've written it there. Okay. You can see it depends. Let me write that down. 3.76 milli electron volt MeV divided by the effective mass divided by the free electron mass. So it's all dimensionless now. Okay. And 10 nanometer width over 10 nanometer. Yeah. Whole square. Square of the width. What does this mean? I mean, these are obviously dimensional quantities now, but if my effective mass in that band is 1, right? I mean, it's like a free electron. It's very heavy, actually. In most semiconductors, it's like 0.01, 0.1, and all that. And the quantum well width, this width here is 10 nanometers. Then the ground state is 3.76 milli electron volts above 0. That's what it means. 3.76 MeV. Not electron volts, milli-electron volts. Right away you can tell me what would be the ground state energy if I had 1 nanometer well. So 1 nanometer well, instead of 10 nanometers, if I had 1 nanometer, it'll go up by a factor of 100, right? So you go from 3.6 MeV to 376 milli-electron volts if I make 10 nanometer to 1 nanometer, right? So you see that, right? I mean, it's square. Square is very important. It goes as the square of the well width. This is a result of the parabolic band structure. If you don't have parabolic, you won't have square, but most semiconductors do have, band gaps that are band gaps are parabolic, so this is very important. Similarly, most semiconductors do not have an effective mass of 1. If you look at, say, gallium arsenide, it's 0.067. It's 0.067. Gallium nitride, 0.2. Right? So that means that factor will bump it up by a factor of 5 or 10 or whatever, something as well, right? So it's very sensitive to effective mass and very sensitive to quantum well width. So the ground state energy. Order of magnitude 10 nanometer and effective mass of 1 will give you 3.76 milli electron volts. So that's important. Okay. If you choose it to be 0.1 effective mass, you can see then you have 37 milliliters. Okay, I mean all these details, but okay. So that's order of magnitude, just to remember. And therefore, let's say I want my ground state energy to be, certain value, 150 millielectron volts above the allowed band edge, above the band edge here, or V is equal to 0. Then you can choose what, let's say you are stuck with a certain effective mass because you chose that material, then you can choose what quantum well width you want. Right? If, on the other hand, some other design, you are constrained in the quantum well width, then you can choose what material you should choose with the effective mass. So these are all the games that you can play with the compound semiconductor design. And then the second level is obviously n squared, so it's 4 times that, the second excited state, and first excited state, and so on. Okay? Is that clear? So again, this is an important order of magnitude to remember. And then you have the odd, even odd, and all that stuff. Okay, any questions here? Yeah.
Is that the energy above 0 or above the conduction band energy?
Good point. Okay, so what we actually solve now is this is the situation. Even if the electron was not in a semiconductor crystal, meaning if you have maybe even if electrons are in vacuum and there are some other metal plates. Okay? So it is the energy, this is the energy above whatever is the situation here. If you have a semiconductor which is gallium arsenide or gallium nitride and something else here, then it is above the conduction band edge of the bulk semiconductor, quantum well, there was no quantum well, but it was infinitely large. It's above that edge energy. I'm going to discuss that part a little bit later as well. But essentially, what you're doing is because of confinement of a layer like gallium arsenide, you can see, right? I mean, that's actually one very good way to look at it is what will happen if I make the quantum well wider and wider and wider. Right? You make it wider. Right? As you go wider and wider, this will gradually go to 0. Right? It will merge with the free electron solution, meaning the ground state is 0. Ground state energy is 0 if you have an infinitely large well. Right? And as you squeeze it, it goes up as L squared. Right? The ground state energy floats up. So, as a result, in that limit, you can see that if I had gallium nitride or gallium arsenide, this will become the band edge of that material. But if you have a quantum well, the band edge is of the semiconductor, its bulk material is still here, but because of quantum confinement, the lowest allowed energy for an electron in that layer is not there anymore, it's there. So that's the meaning. And then you have a gap in between the two. Okay, so more questions. Is that clear? Yeah. Okay, now let's look at the finite well problem, because the infinite well, we develop all these intuitions. What we'll do now is, instead of the infinite well, we're going to change this and make it finite, which is obviously the more realistic situation in most semiconductors. And then we're going to see that the answers will not change much, obviously a little bit more work. And let's say we make it finite now. Yeah. Which is really the case here. If we are looking at the conduction band edge, this is your band offset, delta EC, right? It's the band offset, which is finite. Okay. So let's go back to our way of looking at the problem, and the reason I wrote this all down is because actually kind of most of it stays exactly the same, it doesn't change, except for one thing, right? And maybe you can tell me what happens to, again, this is I'm going to call region 1, region 2, and region 3. Region 2, V of x is still 0, right? V of x is 0, and the solution doesn't change. It's exactly the same. Whenever V of x is 0, Schrodinger equation solution is just that. And you can see now the only place things have changed are 1 and 3. I mean, obviously that's where you change the potential. You've made it finite. V of x is not infinite anymore, it's u naught. And it's u naught. Right? That's the only change, right? And now you can see that the wave function need not go to 0 anymore because it's finite, right? So, and then this part of it, if you've done any quantum, you'll realize it must, if the energy of an electron is below the potential barrier height, then the wave function, instead of going to 0 here, it must actually decay exponentially. That's the solution. Just decay, right? Why? You can actually reason it from here. Right? You can reason it from here, and the way to, again, I'm going to erase this part. Right. So in regions 1 and in region 3, the V of x is basically okay. Let's keep it as so. Let's say in region 3, V of x is u naught, right? And you can rearrange this equation a little bit and write it as d2 psi of x by dx squared is 2 times the mass, effective mass, 2m v minus e or e minus, yeah, over h bar squared psi of x. Okay, just rearrange that equation and then you get that. And when V of x was not 0, then obviously you had a nice, easy solution here. Energy was known and all that. I mean, you found the energy that way. But when a V of x is basically here it's become equal to E in U naught. You can see that this part is kind of a, it's a harmonic, it's basically, it will have sinusoidal solution. Is d2 dx square of something is equal to something times itself, right? So it has like sine and cosine sort of solutions ordinarily, except when, okay, so what I'm saying is if I think there's a negative sign, okay. So if the energy of the electron is below, if the energy we're looking at is below U naught, right? If the energy is below the barrier height, then this term is negative, right? E minus U naught is negative. I think, sorry, I think I did do it upside down, so let me put it this way, okay? So there must be a negative sign there, okay? So, yeah, if you rearrange it, this is what you'll get. Now, if there was no U naught, then this is the equation of a harmonic oscillator, or sorry, it's the equation of a plane oscillation, which is why you get this solution. If there was no potential barrier, the moment you put in the barrier, what I'm trying to say is in regions where energy is lower than the potential barrier height, what the equation now is, it's d2 of something is something which is positive times itself, instead of being negative. If it's negative, you have oscillation. If it is positive, you always have decay. Right? I mean, exponential decay or exponential rise. Okay. So from here, what you realize is that from here itself, you can write that the wave function in region 1 and in region 2 must be equal to some constant. Let's say d. I don't know what he uses. D e to the power minus some kappa x, where kappa is, there's no e to the power I anymore. It's a decaying or a rising function. It's exponential decay or exponential rise. And similarly, for negative x-axis on the left side, you get a e to the power kappa x. So that's the only change. It's the only change. But now you have a little, so instead of writing b and c, we just change these b, c, and d. Okay. So now you have 4 unknowns and 4 coefficients, and again, for a non-trivial solution, you must make sure that their determinant is 0, right? I mean, the coefficients form a determinant which is 0. Once you go through that process, the end result of it is actually very simple. You can kind of match boundary conditions and all that, and here what you match is both the wave function and its derivative. The slopes also match. Right? The slopes must match here because there's no infinite barrier anymore. So the slopes must match. Slopes must match here. So it kind of gracefully kind of goes exponentially decay. Okay. So when you kind of do that, go through that process, you get an equation that's actually analytically not solvable, but numerically you can easily solve it. It's not a problem. So, okay, yeah. And the equation is the following, and that will give you all the finite eigenvalues and eigenfunctions and all that stuff in a realistic, semiconductor quantum well. So the equation you're going to end up with, after you massage it. So again, just for even and odds, you will get this. By the way, there's a little error or a typo in Rocket's book. He has a k in the denominator. It should be, h bar square k square. Just make sure you fix it. There's a typo in the textbook. Okay. So all said and done, the equation you end up with here, I'm going to just write that down. Okay. So h square k square minus 1 is equal to a tangent of k times width of well by 2, or minus cotangent of. This is, as I was mentioning, I mean, this comes from just requiring or demanding that there's a non-trivial solution to it, and then this is what you get. To get a non-trivial solution, your k must satisfy these two relations. Okay, so what you can do now is take this, and this is one of the nice things I'll ask you to do in your assignment problem. So you can basically kind of non-dimensionalize this whole quantity and call this quantity here as some angle theta, tangent of angle theta. K is something you don't know, and the energy is related to h square k square by 2 m star. That's the energy. Why? Because inside here the wave function is just that, and you take, potential is 0, when you take the Schrodinger equation, that's the energy you'll get, a squared k squared by 2m. The moment you can find out what is the k, you just say a squared k squared 2m, you get the energy. Does it make sense? I mean, that's very important point. So this equation is telling you how to find that k that's allowed now in a finite barrier problem. And so you can just define this angle as theta, and you kind of massage this part of it. And also you see there's a k squared, so this is, this will become like a theta square, and there'll be some constant over there, minus 1 square root will be tangent of theta or minus cotangent of theta. So odd branches, even branches, and that sort of thing. So you basically have to plot this and solve this little thingy here. What is this theta naught? So let me just write that down. Theta naught squared probably was written somewhere over there, but it's 2 m star u naught lw, sorry, m star l width of the well squared over 2 h bar squared. Okay, I think this is what it is. Anyway, these are all the properties of the semiconductor: effective mass, conduction band, offset, barrier height. Everything is absorbed into this theta naught. And everything that you do not know is basically just left as one parameter, a single parameter here. Okay, so all said and done, you now plot these. So the left-hand side of it and the right-hand side of it are telling you, wherever they intersect, those are the allowed thetas. And from there you back out, those are the allowed k's. These theta and k are related through that. Right? And then from the k, you can find the energy. So that's the procedure. And when you plot this thing, the general trend of the plot is kind of shown on the top right. I actually do have a little simulation I can show as well, but okay. So what we are changing is theta, which is k times quantum well width over 2. Yeah. And you can basically have pi over 2, pi, 3 pi over 2, and so on. And now on the right side, for example, if you look at the tangent branch, tan theta, tangent branch, right? So tangent blows up at pi by 2. Tan pi by 2 is infinite, right? So it'll basically, yeah, right. So it'll go out like that, and essentially, that's the tangent branch. Cotangent branch is basically tangent branch shifted by, a pi rule. So essentially, you'll basically get another one, and another one, all that stuff. That's right inside. Just to be clear, these are the tan branches, and these are the cot branches, cotangent branches. Okay. Left-hand side, look at this function. It's not, it's so much. This is basically some constant divided by theta square minus 1. Right? So clearly, there's an interesting critical point when theta is equal to theta naught, right? Here, this thing goes to 0, and if theta is larger than theta naught, no real solution. It's square root of some negative number now, right? So what it means is that this function is going to kind of start out at a very large value when theta is small, and it will die somewhere there, and then there's no more real solution. It's cut off, right? So it's basically going to look something like that, and so wherever they intersect, those are the allowed thetas for you. So from here you find theta, back out, find k, plug in into. Essentially, here's your equation for the k and energy, so you can find the energy from it. All right. So let's see. Probably just 5 more minutes. Good. So what I want to show is you can, and please do this. I just wrote it down just before class today, and you can just plug in these values and make a plot. Okay? And here's the plot. Okay? What I really want to show is 2 points, which 2 or 3 points, which are extremely important here. The first point, you might imagine that, remember, the energy values that you get out of here will be, remember we found that for the infinite well, it looks like n squared times E1 infinite, right? For the infinite well, and there are infinite number of levels, right? For a finite well, what we'll find is, basically it's kind of n prime squared over E1 infinite. You can use that still, but this gets slightly renormalized. If the barrier is finite, then the energy levels actually kind of come down a little bit, just slightly so. It'll come down a little bit. And this is a classic, I mean, this is a very standard feature in quantum mechanics. If you let electrons spread out over large distances, they will always lower their energy. Always. Here, you are letting it spread out a little bit because you have a finite width, so it's going to lower its energy. This is a very standard situation. It's going to lower it a little bit, but you can see that you will always have a finite number of states inside, not infinite anymore, because the barrier height is finite. Those are the two major differences. Energies get slightly lowered, and you have a finite number. But one of the interesting questions is, I can make this barrier height very, very small, right? Will I still have a state? And what do you think about that? If I make it really small, will I still have a bound state? Anybody know this answer? Yep.
Yes.
Yes, that's correct. So in one dimension, this answer is actually very much dependent on dimensions. In one dimension, if you have a 1D problem, you are always guaranteed to have one bound state. One. In 2 dimensions, again, you are guaranteed, but that state is going to be very, very shallow, and it's related to superconductivity and all that. 3 dimensions, the answer is not necessarily. 3 dimensions, you can expel a state completely. So you won't bound. But in 1 dimension, no matter how small the barrier height is, you will always have one state. How do we know that? You can see it right from the picture. So the thing is, as you make this theta naught, or the well, smaller and smaller in height, your u naught goes down, so theta naught decreases, right? It decreases. So what's going on is this point is moving to the left, to the left, to the left, right? But no matter how small you are, you will always intersect with that branch of tangent, guaranteed, right? I mean, that's why always you'll have one state here. You cannot get rid of that. And so here's the example. I mean, we are. I think you know exactly what is being plotted here. These are the tan branches. These are the cotangent branches, right? And now what I'm going to do is change my u naught, the barrier height, from 100 MeV, to something. Okay, now I'm going the wrong way. Sorry about that. So no, if I make it larger, on the other hand, you see right now I have 3 bound states. Right? If I make the well larger, you'll have more, right? And that's what this is showing. That if I make the well, this is in electron volts. So if I have, for example, this much, I have 700 millielectron volt height and 10 nanometer well width, then I have 1, 2, 3, 4, exactly 4 states in the well. So you can kind of count that. And then now this is 10 nanometers, and this will change by a large amount if the square of this, right? So as you change the well width, go from 10 nanometer to 1 nanometer, right? 10 nanometer to 1 nanometer, the energy floats up, and you have only one left now in this. I mean, that's the game you play. And then you can kind of find out exactly what are the energy levels and all that by solving. And this solution is exact. There's no approximation in this solution. And then we'll build in further more and more approximations into the solution as we go along. Okay? So, I think so that's an important point. That and the other thing that sometimes is not mentioned is whatever I said, that you are guaranteed to have one state, is only true if your potential is exactly like that we have shown. It's completely symmetric. Both sides have the same barrier. Same barrier. If you allow me to change that condition, meaning on the left side I have a little thicker barrier, a larger barrier than the right hand side, then I can expel that state too. This is a symmetry protected state, meaning if I have the left hand side is slightly bigger than the right hand side, I can actually squeeze this down and I can expel that state. There will be no more bound state. So these are all tricks people play in designing devices. And if you want a bound state, you must choose right barrier heights. If you don't want a bound state, but you still want a quantum well like this, but you don't want a bound state, you can choose an asymmetric barrier and squeeze it and then expel the state. You can actually expel it if it's asymmetric. If it's symmetric, you cannot expel it. And that's kind of interesting point. Okay, so now if you take such a quantum well and you actually do absorption or look at the density of states, I think you see that there are a finite number of states below the barrier here, right? And if the energy of the electron is above that, it doesn't see the well. It's like a 1D free electron now. Right? And in 1D free electron, the density of states of 1D is 1 over square root of energy. But if your energy is lower than the barrier height, then you have discrete states, which is one state. It's like atomic states. So this is the density of states. Very sharp for quantized states, and then this is actually calculated because of some interference and resonances. You get essentially, by the time you reach very high energies, it starts looking like a free electron. There's no more quantum elements. Okay? So this is the density of states. And then, this shows up very nicely in experiments. If you do an experiment, to take a gallium arsenide, do absorption experiment, you'll see these sharp lines because of the quantized states between conduction valence. And then once you reach the larger gap material, you will see a continuum again. So you can see this very clearly. You can change the well widths I had mentioned. If you go from 9 nanometer, you have emission at, say, this one, A. Then you squeeze it and you push up the levels, and then at 2 nanometer, your emission is much out here. So you can change the color of the light coming out just from this quantum confinement, right? And that's not all. You can actually go ahead and play all kinds of games. We are looking at particle in a box in a square well. You don't have to be square. If you want, your energy levels here are separated as n squared, right? So the first to second is very different from second to third. For some applications, you may want that the energy levels are exactly equally spaced. And that we know from quantum mechanics comes if you have a harmonic oscillator, meaning the potential, instead of being like that, is a parabola. Then your energy levels are exactly equally spaced, right? Here, and you can actually grow that. You can start with aluminum arsenide and compositionally change, from, say, 30% aluminum to gallium arsenide and then back to 30%. You continuously change it. You can shape it this way, right? You shape it that way, energy levels will be harmonic oscillator, and you measure, this is experimental data, you can have it uniformly spaced. You can do all this business by the material design after that. Okay, so I think I'm a little bit above time today, but we can end it here, and on Thursday, we'll continue from here and then look at things like superlattices and things like that, but this, I think, is kind of the heart of everything. Once you understand this, the rest of it is a natural consequence of all this stuff. So, and I will post an assignment where you'll get some practice on this. All right, thanks.